Glucose is worth quite a bit of energy. Carbohydrates are worth about, I don't know if you know these things from the back of a package, but a carbohydrate is worth 4 calories in dietary calories, which we all know are not, they're trying to make you feel good because it's off by a factor of 1,000, right? A dietary calorie is really a kilocalorie, and there's 4 joules in a calorie. So, these numbers work out pretty well. When you're burning glucose, this heat here is roughly equivalent. It's off by a little bit from what you see in terms of a calculation of the caloric value of a typical carbohydrate. And that's because whether you burn sugar with like a flame, and this was actually, you wouldn't believe this, but biochemically speaking, people didn't appreciate this at the time, in the 1700s. But if you burn sugar with an open flame and collect that heat, and then you give a guinea pig an equivalent amount of sugar, you'll find that the guinea pig will warm up its surroundings exactly the same amount of heat as burning it in an open flame. Okay? And that's because of the first law of thermodynamics, of course. Energy doesn't just come out of nowhere, but people didn't even understand the concept of energy in the 1700s when thermodynamics was probably getting its early start. All right. So now we want to basically think about the big picture with thermodynamics. It's not just about heat. I mean, in thermodynamics we have heat, which is easy to measure, easy to think about, Q. We can measure heat changes by temperature changes in water. It's pretty straightforward. But thermodynamics ain't all about heat or enthalpy. Now people might be saying, well, what's enthalpy? Well, enthalpy is this heat change at constant pressure. And so at constant pressure, our heat's our enthalpy. The other thing we need to think about is our entropy. And I'll ask you guys to see how well you've been studying for the previous. Does anybody know what's a good definition for entropy? It's a measure of disorder, right? A measure of disorder. That's good. And I like to give this analogy. Got to plan ahead when you use a chalkboard. I like to use this analogy of like when you move into your dorm room, and you set up your closet, you set up your nice bookshelf, your computer, even. How about the desktop on your computer? Have you ever cleaned it up? Has anybody ever cleaned up the desktop of their computer so it's all pretty? And how long does it take once you get into all those term papers and stuff you're downloading from the internet for that thing to get just kludged up with junk, right? And that's okay because that's a computer. You can just wipe all that off and throw it in the trash can. But your closet, man, that thing really gets messy. By the end of the semester, at least for me, I couldn't even find my shoes. I mean, my friends were making fun of me with like unmatched shoes or something like that. Not quite, but and as you know, the reason that that's happening is that you're doing work, you're spending your energy and time studying, right, and working on term papers and studying for Chem 1A lab exam. All right. And because you're doing that, your closet is going to pop. And you know that to reverse that disorder that's happening in your closet, it takes work, right? So to reverse disorder, there is such an idea. To reverse disorder takes work. And what are the units of work? Joules, right? I mean, I don't know, turning a crank. But obviously you're gonna have to fold your socks or whatever, maybe do the laundry, heaven forbid, and all that stuff. And so that takes work. And we know that in order to do work, it requires more energy, more generally, some form of heat, some form of sugar in your case, or food that you eat to do that work. So that's why you need to consider entropy in a reaction. Now, you say, well, what happens when I burn the sugar cube? Well, what happens is you have all these sugar molecules, say, that are all nicely packed together and organized, and you have, these beautiful carbohydrate bonding systems, okay? And it's in a solid, and then you burn it, and you turn it into carbon dioxide and water, and now these molecules have all kinds of, they've become gases, they're wanting to spread out, and you've completely disorganized your sugar molecule. Now it's much a less organized a mixture of gases, okay? So obviously, in that particular case of burning sugar, your disorder term is going to go up. So what we do is we combine heat and entropy into one equation that can tell us how much useful work a system can do, and that's Gibbs free energy. And that's where you have, say, delta G is equal to delta H minus T delta S. And see, this is where you can really connect all this together, because this free energy is the amount of energy, if it's negative, that's the amount of energy that's available to do useful work, okay? And so now you can see how all these concepts connect together. All right, so how much time do we have left? We have 5 minutes before I do the clicker question. And I'm looking at my notes here. So let's flip a board up. Looks like you could do a whole class period on a set of chalkboards. All right. So let's consider ice melting again, okay? Let's consider ice melting. So we already know one term for ice melting, and that's the delta H of fusion. We talked about it. But I'm going to give it to you in different units here. 6 kilojoules per mole, okay? Now there's another term that's going to be useful if we want to know the change in Gibbs free energy for ice melting, and that's the delta S of fusion, okay? And the delta S of fusion for ice is a different unit now, 22 joules per mole Kelvin, okay? Almost like those units for heat capacity. It's not a heat capacity at all. But delta S of fusion, and now we can plug this into our Gibbs free energy equation, delta G equals delta H minus T delta S. And when we do that, you'll find that overall, the free energy for melting ice is minus 556 joules per mole, if I did the math right there. And we're at, remember, your temperature is in Kelvin, not Celsius. And so this means that when I melt ice, it's quite favorable, okay? The entropy has gone up, and yes. I'm sorry, when you freeze ice, no, I don't know, have I screwed this up? I haven't screwed this up. No. All right. All right, so let's just finish up here and think about the direction of a reaction, okay? And people should be pretty comfortable with this already as we've done equilibrium. So if we have a simple reaction like this and we want to know which direction it goes, remember that if the free energy if the free energy is less than 0, then it's going to favor what? C and D or A and B? C and D, right? So products are favored. Okay? Now, there's two other cases here. Greater than 0, then our reaction is going to go backwards, right? Or, sorry, reactants. Reactants are favored. Reactants are favored. And then if the free energy of the reaction is 0, then neither products or reactants are favored. Okay? The reaction is balanced. Okay? So does anybody remember what would happen in terms of the equilibrium constants? And if you've forgotten the relationship between the equilibrium constant and the direction of reaction, remember that there's a nice relationship between free energy and equilibrium. So there's your equilibrium constants, and this is your free energy for your reaction, and they're related by the natural log of the equilibrium constant in RT. Okay? So for equilibrium constants, if your K is greater than 1, or your K is less than 1, or your K is equal to 1, then these cases are synonymous. All right? Because obviously when this number is negative, K has to be positive. If K was less than 1, okay, then that would become a negative number. Negative times a negative would make a positive. So you'd be here. All right? So if K is greater than 1, then you end up with a negative number, a negative number overall, because L and K will be positive. So that will essentially tell you the direction of a reaction, and that's the other thing that's useful for understanding the free energy. You not only get an understanding for how much work this reaction can do, or how much work would have to be done to get the reaction to go in the first place. For example, if I want to turn carbon dioxide and water into sugar and oxygen, does anybody know how that happens? It's photosynthesis, right? So that requires some input of energy. What's the input of energy to drive that reaction in reverse? Sunlight. So that's the importance of knowing the thermodynamics, knowing the free energy. You can tell what direction the reaction can go and how much work can be done. So now we'll try some clicker question. That's pretty straightforward. Here, get out your clicker. I probably can start this computer now. I don't know. Clicker question's pretty easy if you've paid attention and did well probably in your Chem 1A exam. But basically, we're talking about the heat of fusion for water. How much energy would it take to melt 360 grams of ice, given that it's heat of fusion, molar heat of fusion is 6 kilojoules per mole. All right, so fire away and talk amongst yourselves if you'd like. Okay, most of you are doing pretty well here. I have a few people that are confused. Shock words. Oh. Looks like most of you are in the system.
Yeah, well, yeah.
All right, well, I hope. So the first thing you need to do in such a calculation is figure out a way to convert mass to moles. You need the molar mass, water's 18, and then you just do a quick factor labeling. Okay, 360 divided by 18 is 20. 20 times 6 is 120. Answer A. All right. Some of you are picking B and C and D here. No one picked E. That looked really bad, didn't it? I won't put choice E on the exam. But in any case, that's the problem. All right. See you next time.